Let's look at this simple example. And when you and I look at that, we can see an image of a shark. But as far as a computer vision system is concerned, it is just a matrix full of numbers. In fact, this 500 by 500 pixel image contains 250,000 numbers. But human beings looking at this see a distinct object. So the challenge is, how do we find the object in this scene? What we want to be able to do is to find a region within this scene. And we're going to define a region as a group of pixels that are connected to each other, that is, they're next to each other, that have all got the same color. So if we could do that, if for all of the white pixels in this scene, if we could somehow clump them together, then we would be able to find this coherent region, this object, and then we could begin the process of describing what it looks like and where it is within the image. Let's put this into practice. We will load an image, at the shark image, put it into the workspace IM, and we will display it. And these are all very familiar commands to us by now, and we'll have a look at some of the pixel values in here. The black ones have got a value of 0, and the white ones have got a value of 1. We call this a binary image or a logical image. These black pixels with a value of 0 could be considered by MATLAB as false, and these could be considered by MATLAB as true. This image has got only 2 possible pixel values. Now, the first thing that we're going to do is to make a list of all of the pixels within the image. And we're going to do that using MATLAB's built-in find function. And what we're going to do is find all of the pixels who've got a value greater than 0, so that will be the white ones. And it will, for every pixel that it finds, every element of the matrix that it finds, it will return the row coordinate and the column coordinate into those two vectors v and u. So we see that those vectors have got 7,827 rows in them. So there are 7,827 pixels in this image that are greater than 0. So let's have a look at what these coordinates are. So I'm going to display them, and a very large number of numbers just roll past. So let's have a look at some of these numbers. What it's saying is, for instance, the pixel at coordinate 243,170 is a white pixel that belongs to the shark. The pixel at coordinate 244,169 is a white pixel that belongs to the shark. We have a long list of the coordinates of the white pixels. What can we do with these? Well, one thing we can do is find what's the smallest value of the u coordinate. That's the smallest u coordinate in that set of white pixels. And this will be the largest u coordinate, is 245. So this is saying something about the smallest u coordinate of that set of white pixels and the largest. We can do the same in the vertical direction. Say the smallest vertical coordinate and the largest vertical coordinate. So these 4 numbers essentially bound that shark-shaped object. So let's plot a box on the scene, and it's a box whose top left corner is umin and vmin, and its bottom right corner is Umax and Vmax, and we'll plot it in the color green. And what we have done now is to place what we call a bounding box around that set of white pixels. So we're able now to say something about this set of pixels. We're able to say something about where these pixels are within the image. Another thing that we can do is to say, well, what is the center of this group of pixels? And a simple way of doing this is to say the center we could think of as being the average of the minimum and maximum coordinates. So in the horizontal direction, it's that number. In the vertical direction, it would be this number. Now what we can do is we can plot a point at that particular coordinate using the plot point function, passing the u coordinate, the v coordinate, and expects a column vector, and we'll put an asterisk at that location. And now we have drawn a point which in some ways is the center of that object. Actually, it's the center of the box, which is roughly the center of that set of white pixels. We'll be able to do better than that shortly. A technique that's going to be really helpful for us in this endeavor is to compute what are called moments of the image. The moment is given by this equation, and there are 2 parameters to the moment, p and q, and so we refer to the p qth moment of an image. So the moment is simply the sum over all of the pixels in the image of the u coordinate of that pixel to the power of p, the v coordinate to the power of q, multiplied by the value of the pixel at that particular coordinate. And at the moment we're dealing with binary images, so the pixel value is either 0 or 1. A particularly interesting moment is when p equals q equals 0. We call this the 0th moment of the image. And because p and q are 0, then we simply remove them from the summation. And the moment, 0, 0, is simply the sum of the pixel values. Now, if the pixels are either 0 for background or 1 for the object, then the sum of the pixel values is going to be the area of the region. It's going to be the number of bright pixels within the shark that we were just looking at. Another set of very useful moments are the first moments. And these are the moments 1, 0 and the moment 0, 1. And their equations are shown here. We can think of these as weighted averages of the u and v coordinates, weighted by the color of the pixels. So if we take the ratio of the moment 1, 0 by the moment 0, 0, that's the first moment divided by the area, this gives us the coordinates of the centroid of the object. And this is really useful. Now we've found the geometric center of this shark-shaped object. We're beginning to be able to describe it. Let's continue the session that we had earlier. First, we'll compute the 0th moment of the scene using the MPQ function. We pass in the image and we want the 0th moment. The 0th moment is the area or the total number of 1 pixels in the image. And it's the value that we obtained previously. We compute the moment 1, 0. We do that again using the MPQ function, passing the image 1 and 0. So we have this rather large number as a result. Compute the moment 0, 1. MPQ, image 0 and 1. Again, we'll have a very large number. Now what we'll do is compute the centroid of the region. So the u coordinate of the centroid, we'll call it u-cen, is equal to m10 divided by m00, and the v coordinate of the centroid is the moment 0, 1 divided by the 0th moment, and that is the vertical coordinate of the centroid. Let's plot that on the image. We use the plot point function, pass in the u coordinate and the vertical coordinate. We turn it to a column vector, and we'll indicate this one with a circular marker. And here we have the centroid of all of the white pixels within the shark-shaped object. We can see that it's very, very close to the center of the box, and that says something about the fact that this shark object is fairly symmetric.